All right, I think that normal curve problem took longer than I was hoping, so I'm going to have to go pretty fast these last 27 minutes here that we have left in class. A lot to do still. Let's see where we are on the PowerPoint. We're at this formula for the correlation. And again, this is not something that's really used in practice, but it's worth doing to look at why it was positive in our case. And next time I'm also going to show you a graphical way to think about that. But for today we were just fine looking at the numbers. I'm going to skip over this one, but you should certainly think about that. This picture is in your book. Here are the scatter plots that I got for Joe Mauer. We did just calculate the correlation with the formula. I want to remark that I made two graphs here. The first graph I made is batting average of the explanatory variable and his home runs per year, the response variable. The idea being that maybe the number of home runs he is affected by his batting average. Is that really true? That's not necessarily the case, but maybe you have a theory that that's possible. But I could also switch it around. I could put the home runs as the explanatory and batting average as response. Does the number of home runs he gets affect his batting average? Okay. Again, you might say, well, that's kind of fishy. They're not necessarily related, and you might be right. But I'm just emphasizing you can graph it either way. The graphs do look different, but the correlation for both would be the same. That's what I want to remark here. With correlation, I will mention again, it doesn't matter which variable is explanatory and which variable is response. There's no distinction. You get the same correlation either way. With regression, it's different though. We'll come to that. With correlation, it doesn't matter. What I'm showing you here, I did show you last time. I'm going to go through it pretty quick. And it's also in your book. Of course, both variables need to be quantitative, no categorical variables. Favorite pizza doesn't have a value you can plug into your formula. Okay. R stays the same even if we change measurement units. I mentioned, for example, if you switch between meters and feet for length and kilograms and pounds for a weight, it doesn't matter, the correlation would be the same. You can also illustrate this visually, and I made a Mathematica thing to do this, in the following way. I gathered data about, well, this was from the book. This was assets from different countries, GDP per capita means per person, in thousands of dollars. For different countries, here are the countries which you don't need to really focus on. Here's their GDP per capita, thousands of dollars per person. GDP is gross domestic product. It's a measure of the size of the economy. I've also got assets per capita, assets per person. How much wealth does the country have, essentially? GDP is more, I guess, productivity per year, I think. Whereas assets is essentially wealth, though it's not taking into account liabilities. Anyway, don't worry too much about it. What I want to focus on is this graph. This is a graph of that data, bivariate data. I've got the GDP per capita along the horizontal axis and the assets per capita along the vertical axis. Another way to think of the changing measurement units not affecting R is this. As I move this slider, I change the view and I zoom out. It's still the same data set, so it's still got to have the same correlation. However, visually, when your scale is really big like this so that the data are clustered close together in the visual field, people, when they're trying to assess a correlation in their minds, would tend to assess a higher correlation than if you are zoomed in on the data like that. Just visually, it feels like this should be a lower correlation, closer to 0, and this should be a higher correlation, closer to 1. But no, they're the same. Okay? Because changing the scale like this is analogous to changing measurement units. Okay, and that's another way to think about it, and you should know that for a future quiz or test. Okay? These are important things. Again, positive R is positive association, negative R is a negative association. R is always between -1 and 1. Never gets bigger than 1, never gets less than -1. There's no way, at least most of us, can look at the formula for the correlation and prove that so easily. Mathematicians, statisticians have proven it, but that formula that we looked at, it would be, I think, pretty difficult for most of us, maybe even me included, to prove that R can't be bigger than 1 and it can't be less than -1. But it's true. That is the truth. And it measures a linear association. It doesn't say anything about the strength of curve relationships. And it's sensitive to outliers, just like the means and standard deviations are, not resistant. Values close to -1 indicate a strong negative relationship with a negative slope. Values close to +1 indicate a strong positive relationship, linear relationship with a positive slope. 0 means there's no linear relationship. It could still be a strong relationship, just not linear. It could be nonlinear. And R would be close to 0, or could be close to 0. Okay, all important things to know. All right, back to the regression line. Here is the formulas. Let me write them on the board so I can go on to the next slide. Y hat, remember you put this little hat above the Y. Anytime you see a little hat above a variable in statistics, say to yourself, I'm trying to predict or estimate the value of that variable. That's a signifier that statisticians use to say, I'm going to predict or estimate that variable. That's why it's there. B0 plus B1x, you could switch it around. Addition is commutative. You could write this as B1x plus B0. The important thing is B1 is the slope because it's next to the x. And B0 is the intercept because it's not next to the x. It doesn't matter what order you put them. You could see minus signs in here, though, if one of these quantities is negative. You could write it as a subtraction in there. The slope, B1, is the correlation times the standard deviation of the y's divided by the standard deviation of the x's. And the intercept is the mean of the y's minus the slope you just found times the mean of the x's. Order of operations is important, especially with the second one here. This first one, you could divide first, then multiply. You actually could also multiply first in the top and then divide, because these two things are equal. However, in the second one, you've got to multiply first before you subtract. These are the nicest formulas for the slope and intercept when you know the mean of the x's, the mean of the y's, standard deviation of the x's, standard deviation of the y's, and the correlation. If you know those 5 numbers, these are the simplest formulas to use. I'm going to show you some other formulas you can use next time that allow you to compute these things fairly quickly, even when you don't know these 5 numbers. Okay? I'll show you those next time. Not that we're going to focus a ton on those formulas, but I want you to be aware of their existence. Here are facts about least squares of the regression line. They are in your book, but it's probably worth writing down. These are really, really important. Again, just like the correlation ones. Distinction between explanatory and response is essential for regression. It didn't matter for correlation. With correlation, you can switch the x and the y around, you get the same answer. The formula is symmetric in x and y. With regression, however, you must keep track of what's x and what's y. In particular, if you look at this formula, it's not symmetric in x and y. You switch around the sx and the sy, you're going to get a different answer. Not only for the slope, but also ultimately for the intercept. So it's essential in using these formulas that you decide what's explanatory and what's response, or you're told by the book what's explanatory and what's response. Sometimes you have to decide, and sometimes you even have freedom in deciding, and it could go either way. Okay? But sometimes it makes more sense to think of one variable as responding to another, and one variable as explaining the other. It depends on the situation. But you must keep track. The second one is a little bit mysterious, and I don't want to focus on it today. I'll focus on it more next time. Since the formula for the slope is this, it turns out that a change of 1 standard deviation in x corresponds to a change of r standard deviations in y. So that's a little mysterious. You might wonder why. Actually, I would encourage you to think about it before next time. Here's a big hint. When you have a general linear equation, in the typical form you see in a pre-calculus type of course, y equals mx plus b. I hope you've also seen the corresponding equation that the change in y written as delta y, that's not a triangle, that's a capital Greek letter. Delta y is the slope times delta x. You can find the change in y by taking the slope times the change in x. And this is the justification for calling slopes rates of change, okay, and interpreting their meaning. This is part of what explains number 2. It's not the only reason. I would encourage you to see if you can figure out number 2 from that. The other thing I want to point out before going on to the next fact is that since r is between -1 and 1, along a regression line, y always changes by less than x does, at least in standardized units, since r is always between -1 and 1. Y always changes by less than x does along a regression line. And you can take the absolute value of that change if you want as well, because r is less between -1 and 1 in standardized units. Okay, not in actual units, it could change more. But if you standardize it, if you convert to z-scores, essentially, it changes by less. The least squares line always passes through the point whose coordinates are the mean of the x's and the mean of the y's. Note, however, that this is almost never an actual data point. And in fact, for real data, linear regression lines almost never go through any data points exactly. That would be a very rare thing for real data. Okay, I don't know why I put a percentage on it. If I had to guess, I'd say 99.9% of the time with real data, your regression line will not go through any data point exactly. It's just a guess, but effectively almost never. Don't expect it. The square of the correlation, r squared, is actually a better measure of the strength of the linear relationship, though it doesn't tell you whether it's positive or negative. It's got a name, it's called the coefficient of determination. And this last phrase is kind of mysterious. We won't really fully be able to understand it until chapter 10 at the end of the course. It says the value of r squared is the fraction of the variation in the values of y that is explained by, in quotes, that's a very vague kind of phrase, the least squares regression of y on x. Effectively, for now, you can think of this as a better measure of strength. For example, a correlation of 0.5, even though 0.5 is halfway between 0 and 1, that's actually a fairly weak correlation, because 0.5 squared is 0.25, 25%. It's a fairly weak correlation. A moderately strong correlation would have an r squared value close to 0.5, close to 50%. Like 0.7 or negative 0.7. Both of those squared is 0.49, close to 0.5. That's a better indicator of a moderately strong correlation. Right? R squared is a better measure of strength. Not direction, positive or negative, because R squared is positive, whether R itself is positive or negative. You've got to look at the graph to decide whether R itself is positive or negative. To take the plus or minus square root of r squared to find r. That's all you really need to know right now. We'll explain this more fully in chapter 10. What's the regression line used for? It's used to predict or estimate y for a given x. It's also used, typically more accurately, to predict the mean of all the y's for that given x. That's typically a more accurate prediction. I should have said to predict or estimate it there as well. And regression lines are also sometimes, well, at least the slope and the intercept, you focus on those numbers. You want to interpret the real-life meaning of the slope, and less often of the y-intercept. They have real-life meanings sometimes. Making sure you include appropriate units, both to label them correctly and to give you intuition about the meaning. The y-intercept always has units of whatever the units for y are. With Joe Mauer, if you're trying to predict his home run number in a season based on his batting average in a season, the units would be how many home runs. For the slope, it's always the units for y per unit of x. Got that? which is a little funny for batting average and home runs. It would be home runs per point of batting average, which would really be confusing because a 1 point batting average would be 1,000 batting averages. So it's a little, for that situation, it's a bit confusing to talk about the mean and the slope. Might be less confusing if you're predicting the average from the home runs. Maybe I'll focus on that one. That's a little easier to interpret. But it's always units for y per unit of x. You got that? That's key to helping you think about it. And as well as this equation that I circled. The slope helps you estimate the change in y for a given change in x. Multiply the slope times the given change in x. And often you think about the given change in x as being 1, or 1 unit increase. And then the change in y is equal to the slope. But the units are units for y per unit of x. We'll think about examples as we go. Back to Joe Mauer. Turns out if you find the regression line with these equations, or on the spreadsheet, actually, when I made the scatter plot on the spreadsheet, I'll show it to you here real quick. You can add the trend line, which is the regression line, to the picture. If you go to advanced edit here, if it doesn't show up already, there's stuff down here that says you can add the trend line. The default here is none, and if it's set on none, nothing else below will show up. You want to pick linear, and you want to, I think it's good to show r squared, and click on use equation as well. And then you'll see the values of r squared and the regression line equation over here. You have to have this label as well, and you kind of ignore this label here, the home runs being the dots. I mean, that's telling you what the y variable is, but that's a bit confusing because it's not clear that that's supposed to, why is it ignoring the batting average when you look at that dot there? Just focus on this part. Yeah, I couldn't do it with the other part. Got that? It's under advanced edit. So you should be able to do that. And here's again what I got. There's the regression line equation, a slope of 167.8 approximately, and a y-intercept of negative 41.965. Again, the slope and intercept here don't really have much meaning. You're trying to use this equation for typical values of batting averages, between 270, say, and 370. If you happen to know how much his batting average was, how many home runs can you expect? Or better, although a little less valid, maybe I shouldn't say better, more tempting is to use this idea for the next season. To say, okay, in 2016, he hasn't been doing so well these past couple of seasons, Joe Mauer. Not nearly up to snuff. These two dots are the latest 2 seasons. His batting average has been pretty low relative to what it was in the past. However, you say, you're the owner, and you say, Joe, if you can get an average above 300, I'll be happy. And moreover, if you get more than 15 home runs, I'll be happy next season. Maybe I'll pay you a bonus. Okay? Well, based on past data, this is, again, not set in stone. What would you predict for his home run total if his batting average is 300? 0.3 is right about there. Just looking at the line, you'd expect around 8 home runs. You should also be able to use the equation. You'd plug in x equals 0.3. Why don't you go ahead and try that? Plug in x equals 0.3 into that equation. 167.842. So I'm doing it here. If his batting average is 0.3 next season, 300 is what that means. Getting a hit on 3 out of every 10 official at-bats. How many home runs could you expect? I said to expect about 8. Let's see if the formula confirms that. Yes, 8.4. So actually, if his batting average is 300, you'd be happy if he got 10 or more. But maybe you're hoping he can get 15 or more. Another interesting thing about this graph is it shows you how he's better than your typical player. Your typical player, when you look at their batting average and home run total, he's in this kind of range, where he's been recently, the past couple seasons. There's your typical player. So most seasons, his batting average was certainly higher. And at least a couple of seasons, his home run total was higher. This, by the way, was his MVP season. That's an outlier there. He got the MVP. He had a really high batting average, close to 370. And his highest home run total of his career, which I believe was 28. Does that sound right? Okay, which is pretty atypical for him. He is not really a home run hitter. We are in 2015 right now. Those watching in 2069 are interested. Okay. You can also switch it around. You can also try to predict his home runs from his batting average. So now I made home runs the X and the batting average the Y. The equation is different. You should expect it to be different. I switched around the overalls of X and Y. The slope here does have a little bit more understandable meaning, I think. Let's just say it's approximately 0.004. What would the units be? Units for Y per unit of X. That'd be difficult to phrase this. Units of batting average. As a decimal. Might be the best way to phrase that. Units for Y. Per unit of X, which is number of home runs. Telling you, at least for these data, not necessarily for future data, but at least for these data, when you look at the overall pattern, for every extra home run, his batting average went up by 0.004. Like from 280 to 284, for example. For every extra 10 home runs, on average, his batting average went up by 10 times this 0.04, like from 280 to 320. It's the overall trend, essentially. You don't necessarily want to think about it, you know, if he had, whatever, 8 home runs this year and he gets 9 home runs next year, that he's guaranteed to have a 0.004 higher batting average. That's not necessarily the way to interpret it. In some situations you can interpret it that way, but in others, like this one, I don't think you can. Be careful, here's a warning. In general, when you're given a function f of x equals mx plus b, you can find something called the inverse function by swapping around the roles of x and y and solving. And oh, there's a typo here. This should be an x. Right there. Typo, I'll fix it for next time. That's called the inverse function. However, what we are doing with regression is not the same as that. If you think, if I switch around the roles of the home runs and the batting average, then the regression line is going to be the inverse function of the original one, you're wrong. It's not. Okay? If that comment is confusing to you, you don't really need to worry about it. Maybe I won't even mention this next time. But if it was a thought in your mind, it's not the same thing. But again, there is a typo here. This should be an X. For all future video watchers. You should also be able to compute something called residuals. Given a data point, and here I am going to use subscripts xi, yi, we can use the regression line to compute yi hat, in other words, the predicted y from the given x, which is not necessarily a data value. To find y hat, you plug xi into the regression line equation. If you then compute this difference, yi minus yi hat, it's called a residual or prediction error. It's often denoted by the letter e sub I, but don't confuse that with this special number e, which is about 2.71828, that you may have heard of from pre-calculus or calculus. Turns out it's often a good idea to plot the residuals, and I did that down here with the Joe Mauer thing. Home runs on the vertical axis, batting average horizontal. In this new residual graph, batting average is horizontal and the residuals are vertical. You can interpret the residuals as sign distances. If a point is above the regression line, its y coordinate, its yi here is about 8. In fact, I think it was 8. And the corresponding yi hat is the second coordinate of this point on the regression line. That distance, well, that point has a second coordinate around 3 or something. 8 minus 3 is 5. This first residual should be close to 5. And it is, perhaps more like 4.5, but close to 5 up there. That residual value corresponds to this sign distance. The distance between, the vertical distance between this and the regression line is positive because the point is above the regression line. On the other hand, take this point, for example. It's below the regression line, so its sign distance from the regression line is negative. How much negative? By sign, I mean positive or negative. How much negative? This second coordinate's about 13, it looks like. Second coordinate of this point's around 16. 13 minus 16 is around is negative 3. The second coordinate of this point should be close to negative 3, and it looks like it is. So you're plotting those sign distances. Those are called the residuals. Why is this a good idea to make the plot? Because ideally, when you're using regression, what you want to look for is you want to look for random scatter of the residuals along the horizontal line at 0. We don't really see that here. We see a downward trend, then we see an outlier. But in general, what is ideal for using regression is random scatter of the residuals about 0. Hang on, we've still got a couple more minutes. Maybe one more minute. Got a few more important things to say. There are cautions in the book about using correlation and regression. Let me just say you should read about these, think about them, and you'll have some homework problems. There'll be essay-like questions related to these things. Quickly summarize, beware of extrapolation. Trying to use the regression line outside the range of data values. It's dangerous, but I will tell you people try to do it because it's kind of fun and tempting and they just can't resist. Okay? But you as a consumer of information should beware. Also beware of correlations based on averages. They're higher than they would be for individuals. Beware of looking variables like I mentioned last time. And also, like I mentioned last time, association does not imply causation. Make sure you read about these and think about them. Finally, I'm going to let you read about something called simple random sampling, and I'm going to give you a problem or two related to this. Okay, even though we're about out of time. Here's a summary of what it is. You're going to use table B near the back of the book to find what's called a simple random sample. It's not in the very back of the book. It's just near the back. It's a table of random digits. So based on reading, I'm going to expect you to be able to use this table to find what's called a simple random sample that is described here. Okay? You can do it. Okay? It's going to be the start of chapter 3. All right? See you next time.